Determination of the Mohr integral using Simpson's formula and the method of trapezoid. This article 3.9 of the book Mechanical Systems Calculations of the Marine Facilities. Finding the displacement of the mechanical system, any nodes or just the points of the elements of the mechanical system, we usually use a Mohr integral. Mohr integral indicated here as, for example, that displacement in the direction we indicated I is equal to total of the integrals. In the integrand we have the fraction, in the numerator we have the product of two diagrams of the bending moments, and in the denominator we have the product of the factors of the transverse section of the element mechanical system rigidity. And we have as well the variable x-axis, the variable associated with each of elements of mechanical system. As well, we have the limits of the integration. Limits is the beginning of the element mechanical system, and the another limit is the end of the mechanical system. It can be mechanical system element, can be the rod, can be beam, can be etc. Any kind of the disk, geometrically unchangeable element of mechanical system. Anyway, under action of the external load and the support reactions, the mechanical system is have the deformations. The deformations and displacement of points. These two diagrams in the numerator of the integrand is first one is the diagram of the bending moment, and they considered each one element for the considered each one element of the mechanical system. The bending moment of the external force. And the second factor in the numerator is the bending moment and the influence of the unit effort. Unit force, maybe unit moment, applied to the point in the direction in which we are looking for the displacement using the Mohr integral. So to decide Mohr integral and to find the displacement of the point in the vice direction, in direction indicated I, we sometimes can use a direct multiplication of diagrams in the numerator. For example, the denominator we can derive out of the brackets, out of the signs of the integral and the total, out of here. We can simplify this formula like here we have. We derive this rigidity characteristics of the transverse section of the element mechanical system out of the sign of the integral, and we cut it out just because it's out of the interest. We will consider the approaches to determine the numerator and the integral Mohr. And what we have the approaches is not considering so much of the rigidity of the element mechanical system, assuming that perhaps this rigidity is evenly distributed in the element of mechanical system. So not subject for the mathematic transform when finding the magnitude of the integral and the displacement. And we have the adopted approaches to find this product of the diagram besides of direct finding of the Mohr integral. The adopted approaches, for example, could be the use of Vereshchagin rule when one diagram have to be linear at least. We consider that in the article 3.8. And to find the Mohr integral by use of Vereshchagin rule, we consider the area of one of the diagrams, consider the location of the center of the area. Of the other diagram, we usually either have to be linear. It could be diagram maybe of the unit force applied to the direction of the sought displacement of the assigned point of the mechanical system. And the other diagram on direction of the unit effort, unit force, or unit moment. It depends on what we are looking for. Is it a translational displacement of the definite point of mechanical system, or would it be the bending displacement, angular? And for the other diagram, we have to know the magnitude of the diagram in the projection connection to the point of location of the center of the area of the first line diagram. This is a Vereshchagin rule, and besides we have another rules, besides of the direct finding of product of two functions in the integrand and doing the mathematical transform of the integration. And besides of the use of Vereshchagin rule to find the product of the diagram and to find the displacement, we have another widely used approaches. One is the method of Simpson, and another is the trapezoid method. This article, we consider these two approaches to find Mohr integral and to find the displacement of the assigned point of the mechanical system, the direction indicated in the assignment to find the displacement. So the first one is Simpson rule. Simpson rule is to find the integral. We cut out the denominator from this integral and consider only the numerator part of the integral. This is equal to the fraction L divided by 6 and multiplied by brackets. In the brackets we have three summands. The first summand is the product of the magnitude, the ordinate of the first one diagram. The sequence of the diagrams is not so much important in the integral. It could be the product of the diagram of the bending moment under unit force. First and the second will be the diagram of bending moment and action of the external load and support reactions. But the first summand in the brackets is the product of the ordinate. We assume that we do not have the mathematical function of these diagrams as a mathematical equation. We have only the magnitudes at the ends and in the middle of the diagrams. And first factor is the magnitude on the left of one of diagram. Is diagram of the bending moment of the element mechanical system and the action of the external force. Second factor here in the mathematical equation of Simpson rule to find Mohr integral is the second summand here in the brackets. The second factor of first summand in the brackets is the magnitude of the bending moment diagram for the same element, but under the action of the mechanical system, under the action of unit effort, unit force, maybe or unit moment, plus second summand is factor 4 multiplied by the magnitude of the diagram of bending moment of the element mechanical system and action of the external load, and multiplied by the diagram magnitude of the diagram of bending moment of the considered element mechanical system and action of the unit force applied to the assigned point of the mechanical system, which one point we have to find the displacement. And the third summand is the product of the magnitudes of the diagrams of the bending moment and the action of the external force on the another one end of the element mechanical system. And the same as the magnitude of the diagram of the bending moment and action of the unit force. So this is Simpson rule. The Simpson rule gives us the exact decision of the Mohr integral. Only if the curvilinearity of the diagram, it can be curvilinear, the diagrams. If the curvilinearity is not of the bigger power than the square power. So if it is parabolic with a square power of the variable, we can have the exact decision using Simpson rule. If the power of the variable in the nonlinear part of the diagram is more than 2, so 3 or more power of the diagram. In this case, we will have the approximate decision of finding the Mohr integral. If you compare with direct determination Mohr integral, having the mathematical equations of the diagrams of the bending moments. So to use Simpson rule to find Mohr integral magnitude and the displacement of the point in the assigned direction, we don't need to have the area of the diagram. Sometimes it could be of the difficulty. It can be, it's not easy to find the area of the diagram. So in this case, to use the Simpson rule, we only need to have the ordinate of the two diagrams in 3 points each. At the end of the considered element mechanical system and in the middle of the element of the mechanical system. So we can use the Mohr integral Simpson rule. Another one rule widely used is formula of trapezoid to multiply diagrams in the Mohr integral mathematical equation. Formula of trapezoid we can use if the diagrams two are linear. It can be the trapezoid diagram as it indicated on the figure 3.9.2a. They can be the diagrams, even the twisted trapezoid, like on the second picture on the figure 3.9.2b. This is a diagram of bending moment of the considered element mechanical system and the action of the unit force. This example is a twisted diagram. And it can be the triangular diagram, shape of the diagram of the bending moment, not only the trapezoid diagram, but triangular. But in this case, the diagram ordinata, so magnitude of the bending moment and the action of the unit force applied in the direction sought for the displacement finding. This will be 0 for the triangle. And this is a formula of the trapezoid method to determine the integral of product of two diagrams of the bending moment. One, the diagram of the external force, bending moment acting on each element of the mechanical system. The second one is a diagram of the bending moment and the action of the unit force on mechanical system. But this diagram within the limits of the considered each one element of the mechanical system. So the product of diagrams and integral of this integrand equals to the fraction L, length of the span between the ends of the element mechanical system, L divided by 6. And multiplied in the brackets, we have 2 factor multiplied by the magnitude of the bending moment diagram on one end and the first end of the element considered. And if we consider elements of the mechanical system in definite sequence, usually from the point of the finding of displacement to the support, as the displacement of support we assume 0. So the beginning and the end of the element mechanical system we can consider in the definite sequence. So this is the first one element, assuming that the previous one we did consider already. And the next one, and the next point is the second point of the element mechanical system. So this is two products of the magnitude of in the first point of element mechanical system of the ordinata of diagram of bending moment of this element and action of the external load on the mechanical system. The second is the ordinata of the diagram of bending moment of the considered element and action of the unit force applied in the point of finding the displacement in the definite direction assigned. The second is summed in the brackets is we have factor 2 multiplied by the product of magnitude of the bending moment aggregation of the external force in the second point of the element mechanical system, and the product by the magnitude of bending moment diagram for the element at action on the system of the unit force, and plus two summands. This is two summands of the cross multiplication. So with the factors of 1 to and 1 to 1 to first and to second, we can find here the product of magnitude of the bending moment of diagram of the element under action of the external force by the magnitude at the another end of this element of the diagram magnitude under action of the unit force on this element, and plus the magnitude of diagram of the bending moment and action of the external force for this element at the second point of the element at the end of the element, multiplied by the magnitude of the bending moment of the diagram and of the element bending under action of the on the system of the external unit force in the required direction. Well, and if we have this product of two diagrams and determine it, if we would determine this integral, we can find the displacement using Mohr integral equation. So yeah, and this is exactly for the diagrams of the bending moments of the linear shape. Okay, and the exercise. We have the mechanical system, the frame embedded in the point A, and had having the two elements A, B, B, C. BC is element to the end of the element BC in the point C. We have applied a bending moment equal to 7 kilonewton by meter, and the concentrated force equal to horizontal leftward equal to 9 kilonewton. And we have distributed load applied on the element AB of this considered mechanical system. We can say the frame. And the sizes of this mechanical system are length is 4 meters and the h is 2 meters. So we can find the bending moment diagram at the action of the applied external load. We did already that in the point 2.3.7 or 3.8 articles of the book, and besides, we can just a brief repeat how we did find the diagram of the bending moment of this mechanical system at the action of the external load, not unit force, but external load. So the first we have 7 directed leftward on under action of the applied bending moment 7 kilonewton by meter. As we see that we choose that this direction could be negative or the positive magnitude is not so much important. We just need to the sign rule for each of the issue could be relative. So we just need to for each definite one issue obey originally adopted rule for all of efforts applied to the mechanical system. So we have 7. We decided that we do the magnitude to the left as this rotates counterclockwise. And the clockwise rotation we have on behalf of the action of the force concentrated 9 kilonewton. The magnitude increases from the point of the application of force to point B by the arm 2, and this is a linear diagram. So we have this linear diagram, and concentrated force 9 multiplied by the arm 2 is equal 18, and we have another direction of the moment 7 and the action of the force, another influence of other signs to the magnitude of the bending moment. We determine the bending moment diagram on the stretched fibers of each of the as this is usual instructional mechanics on each of the elemental mechanical system. So here we have 18 to multiplied by 9 minus 7 is 11 to the another, and we have the diagram of the bending moment of the element BC of mechanical system at the action of the external load as a linear twisted trapezoid. So the same we have here. We have rigid connection of two elements of mechanical system. This rigid connection transmitted the bending moment, so we have 11 the same on the stretched fibers on the another one, and this on another one element mechanical system, and the distributed load of two, we have the concentrated force we can find here in the middle of 2 meters arm, and 2 by 4 is the magnitude of the concentrated force instead of these two is instead of the distributed load. So H product by 2, 8 is magnitude of concentrated force instead of distributed load. Product by 2, 2 is arm of the action of the concentrated force instead of distributed one. So H by 2 is 16. And 16, the same direction rotation as we have here on behalf of the previous one, the element of mechanical system. So 18 plus 16, 8 concentrated force instead of this one by arm of the half of this span 4 meter. Is 16 plus 11 is 27. This is magnitude of the bending moment at the embedding. And we got that if we have the linear trapezoid, we would have the segment of the parabolic part of this linear trapezoid, and we determined that the parabolic part in accordance with the linear distribution of this force is 4 meter. The formula, we remember that it is equal to the magnitude here, 4 meter, equal to we can from directory find the formula for the parabolic shape determination of ordinate is equal to magnitude of distribution force product by L length of the application squared divided by H. This will be the h of this small segment we have to subtract from the linear shape of the trapezoid. We have to subtract 4. So in the middle we would have 27 plus 11. This will be like 38. 38, if we divide by 2, we will have the middle size of the linear trapezoid for the same one. So as 38 divided by 2 is 19. 19 minus 50 here is the height of the subtracted trapezoid is 4. Is another way to find. Okay, so and to find the Mohr integral by use of the Simpson rule or trapezoid rule, we have to have the diagrams of the bending moment of element of assigned mechanical system and the action of the unit forces. And the action of the first force applied leftward to the point C, we have the diagram linear for the BC element mechanical system, and the arm is 2, this h of this part of the mechanical system, and the magnitude of force is 1, so the bending moment is 2. The rigid connection we have, the bending moment transmitted by through the rigid connection to another one element mechanical system, and we have even distribution of bending moment only acting by cause of the unit force P1, as this force is parallel to AB element mechanical system. So second element of the mechanical system, second unit force applied upward to the point C. So we have to find the displacement of the point C by Simpson rule and by trapezoid rule in 3 directions. In the translational direction leftward, in the translation direction upward. For the upward, this force, unit force, do not act on, do not cause the bending moment of the second element mechanical system BC, as this force is a line of the action coincides with the element BC, so do not cause the bending moment. But for the AB element mechanical system, this cause linearly increased bending moment to the bending A, and the maximal magnitude is 4. And we determine this diagram of the bending moment adduction of unit force applied upward on the stretched fibers of the element AB of the mechanical system, and the unit moment, to find the angle of the bending of the section in the point C of the mechanical system. We apply unit moment. We denote as P, but P not the force is a moment, P3. And this causes the even distribution of the bending moment in the on the element BC, and the same as on the element AB. And as well, we determine the diagrams on stretched fibers of the elements of mechanical system. This is just calculations of this one, magnitudes of these moments. And the calculation as well, the magnitude of the moments on the diagram of the bending of the elements mechanical system and the action of the external force. Okay, so we can find first, for example, the horizontal displacement of the point C using the Simpson method and using the trapezoid rule. So here's the first one is Simpson rule. We derive out of the bracket the rigidity. 4 is the length of the first element mechanical system AB, and the denominator we have as a characteristics of rigidity of the transverse section of the first element, but for the assigned mechanical system, the rigidity, characteristic elasticity modulus, and the moment of the inertia of the transverse section of the mechanical system for each elements are assigned to be equal. So we have in the first summand and the second one. This first summand is the determination of displacement due to of the point C due to deformation of the AB element mechanical system. The second one is the deformation assessment of the BC element mechanical system. Exactly, we can say that the first element is AB, the second element is BC. This is easy to explain. If we just will count the elements in the sequence starting from the embedding of the mechanical system. So in the accordance to the Simpson rule, in the brackets we have the product of the diagrams. The first is the magnitude of the bending moment on the diagram of the external load here and then embedding, and we find the multiplication of this by 2. 2 is magnitude of the bending moment of the diagram of the action of the horizontal force applied to point C in the direction in which we look the horizontal displacement of the point C. So we found the first one summand in the bracket. The second is 4 is factor of Simpson rule. 15 product by 2. 2 is magnitude in the middle of the diagram, but the magnitude of the diagram of the bending moment and action of the external force is 15. In the middle of the first, we say first is AB element mechanical system. And plus 11 multiplied by 11 is magnitude on the left hand of the diagram of the bending moment of the mechanical system element first AB on the action of the external load, and 2 is the magnitude of the bending moment of the diagram of bending of the mechanical system and action of a unit force applied point C in the direction we look for the displacement of the point C. Okay, and now we have the second summand. Second summand is for the second element mechanical system BC. The length of the second element is 2 meters. 6 is a factor of Simpson rule. E, I is elasticity modulus, and the moment inertia of the transverse section of the second element mechanical system multiplied by the brackets. In the brackets we have 11 multiplied by 2. 11 is 11 here for the second element mechanical system. 11 is magnitude of is on the same. It bent on the same direction as on the previous one element mechanical system. We have 11 on the right, applied on the stretched fibers of the second leg or the second element BC of the mechanical system. This multiplied by 2. 2 is the magnitude of bending moment action of the unit force in the required direction to the point C. Plus we find 4 force factor of the Simpson rule. 2 is a magnitude of the bending moment on the diagram. Here in the middle, we can find the middle one. The rule of Simpson we can apply as well to the twisted trapezoid. This is twisted. This magnitudes of another signs. If we assume that 11 is positive, so 7 have to be negative. But this size can be 2. We can find as 11 plus 7, no, but not plus, but minus 7 is in the another magnitude direction is equal to with another sign. So 11 minus 7 is 4 divided by 2. We can find the middle magnitude of the bending moment here. 11 minus 7 divided by 2 is 2. 2 is magnitude, and we have to product this in the middle of the diagram of the bending moment and the unit forces with a maximum of triangle shape with the maximal base of this triangle. We have in the middle the magnitude 1, so we have product of 2 by 1 in the middle of the second element of the mechanical system, and other we have to do the product minus by 0. 0 is the magnitude of the diagram of the bending moment direction of the unit force in the point C. 0 from 0 to 2 is linear diagram, and minus 7 to another direction magnitude of the bending. If you compare with 11 and assume this positive, this is negative in this case. So after the calculation of this equation, we can find that the displacement is 140.67 divided by characteristics of the rigidity of the mechanical system transverse section. If we use an international system of units displacement, we can find, for example, in the meter. This is megapascal dimension in accordance modulus of the elasticity in accordance with the international system of units. This is moment of the inertia of transverse section of the elements of equal for each of 2 elements of this mechanical system, and this is a unit of the length powered by 4 in 4th degree. So it could be meter in 4th degree example. So we have to obey the units of the displacement to find in what units we will have the result of the displacement of horizontal displacement got by Simpson rule, by Mohr integral finding by Simpson rule for the leftward displacement of the point C. So besides that, we can use the formula of the trapezoid to find the bending moment, to find the horizontal displacement too. But for the first leg of the mechanical system, we cannot use the trapezoid rule. As for trapezoid, the assume is that for all of the elements mechanical system, the bending moment diagrams have to be linear. As for the action of the external load, the same as for the action of the unit force. So we can combine 2 approaches. The first amount in the determination of the displacement of the same point, but not by the method of the Simpson, but by the method of the trapezoid. The first one determination of the point C leftward by the action of the distributed load on the first element AB of the mechanical system, we would remain the same determination as we did with Simpson rule. By Simpson rule, as a Simpson rule, we can use as well as for linear shape of the bending moment diagrams, the same as non-linear shape. And if a shape corresponds for the parabolic shape of the degree no more than 2, this gives us the exact solution of the Mohr integral. If more than 2, the degree of the variable in the parabolic segment, this can give us the approximal decision the Simpson rule will give us. In this definite one, we have the dependence parabolic in the square degree here as bending moment and action of even distributed force is proportional to the x, the line of the application of the distributed force in the second in the power of 2. So we can have the exact decision, and the first summand will remain the same as in the previous formula, although we remember that it's not for sure 100% use of the trapezoid rule. But the second summand we can determine by use of the trapezoid rule due to both diagrams, as the diagram of the bending of the second element mechanical system BC and the action of the external load. The diagram is linear, although twisted trapezoid, but actually linear. And the diagram of the bending moment and the action of the unit force applied in the direction leftward in the point C. So we will not consider the first one summoned, just only the second one. The second one summoned the common factor we derive out of the brackets. In the brackets we have 2 product by 11 by 2. This is the product of the magnitudes of the diagrams of the bending moment. So for the second, we first consider the same as by the Simpson rule, as this is non-linear, but the second one is linear. We use the trapezoid rule. In the brackets we have for summoned -7 product by 11. We have oh, excuse me, we have 2, this factor of the trapezoid rule, product by 11, product by 2. So 2 is the magnitude of the bending moment and action of the unit force, and 11 the magnitude of the bending and action of the external load in the point C for the element BC, second element of the mechanical system. Okay, so second summand we have minus 2 factor of trapezoid rule. For the first 2 summands we have 2 factors. Factor 2 for the first one, factor 2 for the second one. Product by 7 by 0. 7, why minus? Minus this because the, this because the diagram of the bending moment and action of the external load for the second changes sign. From 11, we assume that 11 is positive. In this way, we have considered 7 as negative. -7, we have in the trapezoid rule the factor 2 product by -7, so it is minus. And we have 0. 0 is magnitude of the bending moment and the action of the unit force in the point C. So we have 0, although we remain the summand in the mathematical equation. Hence, we have 0 factor as well. Plus 11 product by 0 is cross multiplication. 11 is one magnitude of the bending moment and action of the external load, and the cross product by the magnitude of the moment and action of unit force, but at the another end of the considered element of the mechanical system. This plus as 11 is with a plus, and -7, 7 is of the another direction of the bending product by 2. -7, -7, and the product we have in the trapezoid rule next to summons in the brackets as the cross multiplication of the bending moments of the diagrams of bending under external load and the diagram of the bending under the unit force. So we have here 2 the other end, and on the other end we have -7. We have -7. This is last summand in the brackets, and after the calculations we find the same magnitude, that the displacement of first point finding by use of the trapezoid rule, but not for 100% trapezoid as the first summand in the general equation. We remain from the Simpson rule as the first. We cannot use the trapezoid rule for nonlinear diagrams. The first diagram nonlinear, so we remain the first summand. And the second summand we got just to indicate the way of the use of trapezoid rule as a trapezoid. And we have each is equal to fraction 140.67, the same as the previous one, divided by E, elasticity modulus, and by moment of the inertia of the transverse section of the mechanical system. For the issue, we assume that these factors of elasticity and the factor of the shape, like a moment of the size and the shape of the transverse section, have to be specified in the assignment. Okay, next step, vertical displacement of the point C. Vertical, we assume the action of unit force on the point C upward. So we're looking for the vertical displacement. This force caused the bending moment only as the line of action of force coincides with the second one element of mechanical system BC. So this force causes only the bending moment in the first one element. The maximal magnitude of the magnitude of the force is 1 and the arm is 4. The size of the mechanical system, the whites is 4. So we have maximal. And the sign of this diagram is negative if we assume this as well as on the stretched fiber. So the first element we determine the diagram, but this is on the another side of the mechanical system. If we assume the first one positive, this one have to be negative. Okay. And what we have using Simpson's rule, we first have to do in product of 2 diagrams by the rule of Simpson. For the first one element mechanical system AB, we have -27 as magnitude on the lower diagram on the left, -27. Product by 4. 4 is the magnitude of the diagram and action of the unit force, with minus as the other signs. The first rotation, the bending of the mechanical system element 1 is counterclockwise. On the second we have, the first is rotation clockwise. Clockwise as the diagram is determined on the stretched fibers. So there's first element mechanical system, and the second is the rotation counterclockwise. We assume this diagrams of other signs, so the product equal to with the -4. For the middle, we have the same. We have as 4 is factor of the Simpson rule. Product by 15 is the magnitude of the bending moment for the first element of mechanical system in the middle, and product by 2 is the magnitude of bending moment in the middle of the diagram of the bending of the first element of mechanical system and action of unit force directed upward applied to point C. And we have +11 product by 0. 11, we have here ordinate on the next end, the product by 0. 0 is because we have here. We don't use the sign. This is magnitude of the diagram of the bending moment at the action of the unit force applied upward to the point C. And we don't use the minus sign, as 0 not so much important, is a minus or plus. So after the substitute of toll, after doing calculations, we found that the displacement in the upward direction of the point C and action of the external load is minus fraction 152 divided by characteristics of the rigidity of the transverse section of the mechanical system, elasticity modulus, and the moment of the inertia of the transverse section. Next is we consider the rotation of the section point C when we by use angle of rotation determination using the Simpson method and the method of trapezoid. And as well, formula is the same approach. We have to use the bending moment diagram, and we have to use the diagram of the bending moment at the action of the unit moment. P3 is not a force but a moment. Okay, and this is a delta upper size ledger 3, and we derive the common factor out of the brackets. We consider two elements of the mechanical system, the first one from the point A to B, the second one from B to C. And we, to find the Mohr integral, we use Simpson rule first. This is a product of minus 27 by 1. Why minus? Minus just because the magnitude we assume positive when the diagram is for the moment rotation clockwise. And in this definite one case, we have the diagram of unit moment applied in the direction of finding angular bending of the section in the point C. But this moment applied P3 unit moment rotate counterclockwise. So the stretched fibers are below the first and to the left of the second elements of the mechanical system. So we have minus minus 11 product by 2. 11 is excuse me, minus 27 product by 1. 1 is the magnitude of the bending moment, and as well we have minus 4. 4 is factor of Simpson rule. Product by 15 and product by 1. 15 is the magnitude of the bending moment and the action of the external load in the middle of the first element mechanical system between the points A and C, A and B, and minus 11 product by 1. 1 is the magnitude in each case of the diagram of the bending moment at the action of the unit bending moment distributed evenly to both legs. And we assume negative as they act contrary to the positive assumed clockwise for the lower diagram. Positive we assume clockwise bending. Okay, and for the second element mechanical system we have as well, we have it's only one plus we have, as we finding product in the third summand of two negative magnitudes. So negative magnitude and action of the external load, and the negative magnitude 1 and action of the unit bending moment. So the last summand in the brackets is positive. Minus 1 multiplied by minus 1 equal to plus 1. So in the middle of the, we have as well the magnitude of the bending moment of the twisted shape bending moment diagram at the action of the external load. We assume the linearity of this diagram, and we find in the middle that the magnitude of the bending moment is equal to 2, and minus 1 is this minus of this one is minus 1, the magnitude of the diagram of the bending moment at the action of the unit moment. And we can find together that this corresponds to minus 69.33 divided by characteristics of rigidity and visual rigidity of transverse section of the mechanical system elements equal for each of two elements. And we as well have to obey the dimensions rule for international system. We can use we can find in the meters as we used it all others in the Newton meter and Pascal of the elasticity modulus, and meter in the power by the power of 4. Only one small error, sorry about that. This have to be 1, not 2 by 1. 2 by 1, the product, the magnitude of the bending moment diagram have to be 1, not 2. This is error. This is the description error. This one. Okay, and next we can find the angular displacement of the section C, the same angle of the section C turned, but this is another one. Small error in the description have not to be 1, but 3. Number 3 have to be here. We derive as well the common factor out of the brackets, and in the brackets we have the first summand will remain the same as when using Simpson rule. Why? This generally is a rule finding of the displacement angular by the trapezoid rule. But for the first element mechanical system from A to B, we have nonlinear parabolic shape of the diagram of the bending moment. So for the parabolic shape is appropriate the use of Simpson rule, because as well we account the magnitudes of the bending moment of the under action of the external load at the ends of the element mechanical system and in the middle. So we have 3 magnitudes, and for the Simpson, for trapezoid rule, we have only 2 magnitudes at the ends of the element of the mechanical system. Okay, so this first summand is the same as the previous one. We remember that we have adopt the index here 3, as here this is a little bit mistakeful one. Okay, plus the second summand, we derived the common factor out of the brackets. In the brackets, we have the products of the diagrams, the products of the ordinates at the ends of the diagrams. We consider this second element mechanical system and that linear trapezoid shape diagram, twisted trapezoid, is plus 11 minus 7 magnitudes at the ends of the diagram. And this all minus 1 we have for evenly distributed bending moment for all under action of the unit force applied the rotation counterclockwise. The point C, this is a diagram of the bending moment evenly distributed. So, and we have here in the brackets 2 is factor of the trapezoid rule, product by 11. 11 is the magnitude of the bending moment of 11 on the diagram. 11, this one of the diagram of the second element of the mechanical system. Magnitude 11 is at the point B, and 1 is magnitude of diagram of the bending moment and action of unit bending moment. This is minus 1. Why minus? Because we assume that this one plus, as this 2 moment directed in the opposite directions. This bending moment and action of unit moment and this bending moment and action of external load have the opposite signs. Yes, this is positive. The second one have to be negative. So we do minus to all the first summand in the brackets, plus 2 product by 7 is negative, and 1 is negative, is magnitudes of the moments of the C point of the second element of mechanical system. And the action of the external load we have 7, and then the action of the unit force, unit moment bending at the point C we have 1. So these 2 rotates counterclockwise. That is all 2 negatives, but 2 negatives gives us plus, the product of 2 negatives. And 2 is a factor of the trapezoid rule method. Minus, this minus comes from 1. 1 is minus 1. So 11 we generally have the plus sign of the load diagram of the bending moment and the action of the external load, and for the unit bending moment we have minus 1 directed another than the diagram of the bending and the action of the external load. And we have minus comes from 1 is another And we have plus. Plus is because these two magnitudes of the bending moment at the action of the external force and the bending moment action of the unit bending moment in the point C, they two both are of the minus sign. So products of two minuses gives us plus. And in the after calculation, we have that the same magnitude of the bending angle of the bending angle of in the point C have to be delta 3. Let me remind, please, sorry. This will be the same magnitude of the bending moment angle of the section C torn under action of the external load. And questions and comments. Determination of Mohr integral by multiplying of diagrams using Simpson rule. Using Simpson rule, we have the common factor, commonest fraction of for each of element of mechanical system. For each length of the element mechanical system, the common factor is out of the brackets. We have L divided by 6. And in the brackets for Mohr, we have the products of the magnitudes. We don't need to find the areas and don't need to find the location of the center of the areas, as we have to do when using Vereshchagin rule. For the Mohr, we just only have to have the magnitudes of the bending moments at the beginning of the element, in the middle of the element, and at the end of the element. We have to have the magnitudes of the bending moment at the action of the external load and on the action of the unit force. And the summands have the factors inside of the brackets. The first summand with 1 factor, the last summand third is 1 factor, and the middle summand we have with 4 factor. So 4 factor of the multiplication of the magnitudes of the bending moment in the middle, on the action of the external load and then the action of the unit force in the direction we look for the displacement. Finding the area of diagram and the position of the center of the area using Simpson formula. As well, we can find the position of center of area and as well as the area of the diagram. But we no need, this is not required to find the displacement. If we have the displacement got by Vereshchagin rule and we have the displacement got by the Simpson rule, perhaps we can do have the equation to find the area of the diagram and position of center of its area using Simpson formula at first. Determination of Mohr integral by multiplying the diagrams according to the rule of trapezoid, provided the diagrams are linear. The rule of trapezoid to find the Mohr integral we can use only for the linear shape of the diagram. Even if the diagrams are not trapezoids but the twisted trapezoids, so with sides of the trapezoid of other signs, twisted trapezoid, or it could be the diagram of triangular shape, is like a trapezoid with one of the sides equal to 0. So the finding by the trapezoid rule for the linear shape of the diagram of the bending moment of the bending of the mechanical system and the action of the external force and the action of the unit force in the required direction for the assigned point for determination of the displacement of this point, angular displacement or maybe linear displacement. We have the common factor, the same factor as in the Simpson rule. Common factor consists the length for each of the element of mechanical system. Determination by the trapezoid rule consists the common factor of the length derived out of the brackets, length divided by 6. And in the brackets we have 4 summands. The first summand is first 2 summands has factors each 2, and the first 2 summands is the product of the magnitudes of diagrams of bending moment and action of the external load and the action of the unit force. at the ends of the element considered mechanical system. And the last two summands is cross multiplication of one magnitude of the bending moment from the beginning of the diagram for the direction of the external load, and the second factor in the product is the magnitude at the end of the diagram and the action of unit force, and the last summand is the product of the magnitudes of diagrams for cross multiplication. One magnitude is the magnitude bending moment of the lower diagram at the end of the diagram, and the second factor in the last summand is the magnitude of the diagram of bending moment at the action of the unit effort. Okay. 3.9.4 finding linear and angular displacement of specified point of the mechanical system using Mohr integral and the Simpson method to produce the diagram, the Mohr integral. We can use Simpson method to determine the instead of direct product of mathematical functions, if we have of mathematical functions of the diagrams of the bending moment and action of the external load and the action of the unit force, and instead of use of the Vereshchagin rule by the product of the area of one of diagrams for each of the considered elements of the mechanical system by the magnitude of the another one diagram could be first one diagram of the bending and action of the external load, and second one and the action of the unit effort in the direction of the displacement we have to determine. And instead of that, we can use the only the magnitudes of ordinates of the bending, with not bending moment of each of diagrams, whether on the action of the external load or the action of the unit force. For the Simpson rule, we have to use three magnitudes at the ends of each three magnitudes of the bending moment diagrams at the ends of the considered element of mechanical system and in the middle. And this Simpson rule gives us the exact decision, yes, if only the curvilinearity of the diagram is not more than second degree of the variable. So if the parabolic was the second power, the parabolicity of the diagrams of the bending moment, Simpson rule gives us exact decision. And if the power is more than 2, the Simpson rule gives us the approximate decision of the displacement and the action of the on the mechanical system of the external load. Finding linear 3.9.5. Finding linear displacement of specified point of the mechanical system using Mohr integral and the method of trapezoid, provided the diagrams are linear for their multiplication in Mohr integral. If we have the diagrams of the bending of the mechanical system element and the action of the external load linear, and the diagram linear of the bending of the element and the action of the unit force applied to the point in the direction which we have to find the displacement, we can use the trapezoid rule. This is a little bit easier sometimes, as for the trapezoid rule we no need to have the magnitudes of the diagram of bending moment in the middle, just only at the ends of the diagram of the each of two diagrams, whether under influence of the external force or under influence of the unit force and applied in the definite direction. Thank you.